welcome to the Deep Dive. We jump into the biggest stories to get you up to speed, fast. Today, something that honestly feels like science fiction becoming fact, capturing the sun's power right here on Earth. It's been this far-off dream for ages, hasn't it? But what if that dream is actually starting to take shape, like right now? We're zeroing in on China's huge achievement with its artificial sun reactor. And this deep dive, it's specifically for you if you love getting into the nitty-gritty of major science breakthroughs. We'll unpack what this is, why it's potentially game-changing for global energy, and the specific tech steps that have everyone talking. We're talking about the Experimental Advanced Superconducting Tokamak East for short. Think of a giant magnetic donut designed to copy the sun's fusion process. And it just did something genuinely amazing. It held super-hot plasma stable for 1,066 seconds. That's, well, it's a new world record, pushing the limits. Okay, before we get fully into the science, just a quick reminder. If you enjoy what we do here, please hit like, subscribe, maybe the notification bell, so you don't miss our next deep dive. Any affiliate links are down in the show notes. And hey, we really want to know what you want us to cover next. Drop your ideas in the comments.
It really is a landmark moment, no question. When we talk about fusion energy, people often call it the Holy Grail, right? And for good reason. The promise is just enormous. Practically limitless clean power. Imagine energy without the carbon emissions, with very little radioactive waste, using fuel basically found in seawater. So yeah, this isn't just a lab result, it's a big step toward that future.
That is a powerful picture. So, okay, let's get to the core of it. What does it really mean to build an artificial sun, and why is it so incredibly hard?
Well, fundamentally, nuclear fusion is what powers our sun. It's the opposite of nuclear fission, which is what current nuclear plants do, splitting heavy atoms. Fusion forces light atoms, usually types of hydrogen like deuterium and tritium, to actually merge together. When they fuse, a tiny bit of mass converts into a massive amount of energy. You know, Einstein's EMCSE, right? It's incredibly efficient, potentially offering vast energy from, well, very little fuel.
And just recreating that process here, the scale of the challenge is hard to wrap your head around. Inside that East reactor, temperatures have to hit over 180 million degrees Fahrenheit. Just think that's more than 10 times hotter than the core of the actual sun. But getting it hot is like only step one, right? The really crucial part, the record, is that East held that plasma, that incredibly hot stuff, for 1,066 seconds. That's almost 18 minutes. Sustained. For anyone who follows fusion, the big hurdle isn't just hitting the temperature, it's stopping tiny instabilities from crashing the whole thing. They call it a disruption. Holding it that long suggests, well, a whole new level of control.
Exactly. Plasma isn't just superheated gas. It's this unique state of matter. Its ionized electrons are stripped from atoms, creating this soup of charged particles. So the massive task is not just making it that hot, but dynamically holding on to it, keeping this super reactive, energetic plasma stable and contained for a long time. That stability, it's absolutely non-negotiable for actually generating power someday. Without that precise control, the reaction just stops. Or worse, it could damage the machine.
Okay, so knowing how tough that is, how did they actually manage it? What were the key tech improvements behind this record? Because like you said, this wasn't just luck. East started up back in 2006. This must be the result of, what, years of constant upgrades?
You're absolutely right. This record comes directly from really deliberate, continuous engineering work over more than a decade. And what's fascinating is a huge part of it is a massively upgraded heating system. This system pumps an incredible amount of power into the plasma. Get this, the power output is comparable to almost 70,000 standard household microwave ovens all running at once. We're talking sophisticated techniques, things like electron cyclotron resonance heating, neutral beam injection, all tuned perfectly to get the plasma super hot. But it's not just raw power. That heating works hand in hand with much, much better real-time control systems. These systems use advanced sensors, super fast feedback loops, some even use AI, machine learning to constantly watch the plasma's behavior. This lets the scientists not just reach, but maintain those extreme temperatures needed for fusion, and crucially, keep the plasma stable inside its magnetic field. It's like conducting a tiny, contained star.
Yeah.
And doing it for so long, that's a real leap.
And that control, that precision, that's really what opens the door to continuous power, isn't it? This is where it gets really interesting. That level of control isn't just cool science. It's fundamental to how a future fusion power plant would actually operate. It's about making it reliable, sustainable, not just a quick flash. Now, East is clearly a massive success for China, but this whole fusion quest is bigger than any one country, right? It feels like a global race, but also maybe a global collaboration. What's China's role in that bigger international picture?
That's a really important point. Yes, East is a national achievement, but it's also a major contribution to the global fusion effort. China is a key player in ITER, the International Thermonuclear Experimental Reactor, that huge project being built down in southern France. ITER is massive, a joint effort by 35 nations aiming to build the world's largest fusion experiment. And China is contributing about 9% of the construction and operation effort, so a significant partner. And the knowledge, the data coming out of East, it's incredibly valuable. It doesn't just stay in China. It directly helps ITER solve problems. It also feeds into other projects like China's own next step reactor, CFETR, the China Fusion Engineering Test Reactor. For example, East's long pulse experiments provide vital data on how materials behave under sustained plasma exposure, which is critical for designing reactors like ITER and CFTR that need to run for much longer periods. It's this, sharing of knowledge that pushes everything forward.
Right, CFETR. I read that it has some really ambitious goals, like building directly on East and ITER, initially aiming for 200 megawatts of fusion power, then maybe over a gigawatt later. That sounds like bridging the gap between experiment and actual power plant.
Exactly. It's designed precisely for that, to bridge the gap between ITER's scientific proof of principle and a commercially viable fusion power station. And Song Yuntao, who directs the Institute of Plasma Physics where East is located, he's been very clear about this. He stresses the need to use facilities like East to broaden international collaboration, to actually get fusion energy working practically for everyone. If you step back and look at the big picture, yeah, it's absolutely a worldwide effort. No single country has all the answers or resources. It takes everyone working together.
So bringing it all together, all these incredible steps forward, what does this actually mean for, well, for us? For our energy future? Beyond the labs and the scientific papers, what's the real-world promise here?
Well, the promise is potentially transformative. Fusion could tackle several of our biggest global energy problems at once. It offers a power source that's essentially inexhaustible, uses readily available fuel, and crucially produces zero greenhouse gases, so it could be a massive tool against climate change. Plus, it could mean energy security for countries everywhere, reducing that dependence on fossil fuels, which are, finite and often caught up in geopolitics. And compared to traditional nuclear fission, the waste products are much less problematic, shorter-lived radioactivity, no long-term storage headache.
And achievements like East's record, they really do make that fusion-powered future feel closer. It's not just theory anymore, it's tangible progress. You can see the path forward.
Absolutely, and they're not stopping. There are new experimental facilities already being built in Hefei, right near East. These are designed specifically to build on East's successes, to refine the technology further and really speed up the journey towards practical fusion power. Now, don't get me wrong, there are still huge engineering challenges, managing the intense neutron bombardment on materials, perfecting the tritium fuel cycle. Big hurdles remain. But every record like this, every stable, long-duration plasma shot, it chips away at those challenges. It brings that future closer.
Okay, so wrapping up our deep dive today, key takeaways. China's East reactor smashed a world record for sustained fusion plasma. We looked at the smart tech innovations behind it, the heating, the control systems, and we talked about how vital international teamwork, like with ITER, is to this whole quest.
And let's not forget the ultimate goal, fusion energy's huge potential. Clean, sustainable, virtually limitless power. It's moving from distant dream towards achievable reality, one step at a time.
So here's something for you to think about. As we stand right on the edge of what could be a new energy era, how quickly can we actually make the shift to fusion power? And what steps do we collectively, globally need to take to make sure it happens successfully and fairly? Keep asking questions, stay curious, and join us next time on The Deep Dive. And please, if you found this useful, like, subscribe, and maybe share it with someone else who loves to learn.